Okay, so hi everybody, welcome back. In this video, we're going to continue our chapter 36 lecture on the theory of relativity. And where we left off in the last video was we went through a history of the development of the theory and what sort of motivated Einstein to formulate the theory. And then we talked about time dilation. So we're going to start here with a practice question that deals with time dilation. So a team of astronauts is sent on a rocket on a mission to deep space. After a short period of acceleration, the rocket moves away from the Earth at a constant speed of 0.590 c, so 95% of the speed of light. According to observers on Earth, 4.75 years have passed since the team left on their mission. But according to the astronauts in the rocket, how long have they been gone on their mission? So pause the video, try to work this out, and then we'll go through it together. Okay, so we'll start by drawing a picture of the situation here. We have the Earth, and this set of coordinates that is attached to the Earth and moving along with the Earth is the Earth frame of reference. Okay, then we have the ship. And the ship is moving relative to the Earth away from it at 0.95 c. And this set of coordinates that is attached to the ship and moving along with the ship is the ship frame of reference. So that's basically what's going on here. Now, we're referring to some sort of time interval in this problem, some sort of delta t, okay? Which, of course, is the difference between two times, TB and TA, where A and B are two different events that happen. Now, we're talking about how long the ship has been gone for, right? So, of course, the first event, event A, is the ship leaves the Earth. What about event B? Well, to make this a little bit more visual, I'm going to put a sign here. Just imagine a signpost floating out in space, okay? And we'll just say that event B is when the ship passes the sign. Okay? So delta t is just how much time passes from when the ship leaves the Earth and when the ship passes the sign. And of course, these two frames of reference, the Earth frame and the ship frame, are not going to agree on that time interval, okay? So if we think about it, in the ship frame, the two events happen at the same location. Okay, in the ship frame, the ship leaves the Earth at that location, basically the origin of the coordinate system. And then when it passes over the sign, that also happens at the origin of the coordinate system. So the two events happen at the same location. So this would be what we call the proper frame. And the time in this frame is what we call the proper time, delta t naught, and we actually don't know what that is. Now in the Earth frame, we do know the time interval. The time interval delta t in the Earth frame is 4.75 years. Okay, so 4.75 years pass according to the Earth frame. We want to know how much time passes according to the ship frame. And it's, again, really important to see here that the proper time is not 4.75 years. The proper time is unknown, and we're solving for it. Okay? So our formula for time dilation goes like this. delta t is equal to gamma times delta t naught. If we want to solve for delta t naught, we're going to divide by gamma. So we have delta t divided by gamma. But remember, gamma is equal to 1 over the square root of 1 minus v squared over c squared. So what we're solving for, delta t naught, would just be delta t times the square root of 1 minus v squared over c squared. Okay, so now let's plug the numbers in. For delta t, we have 4.75 years times the square root of 1 minus v squared over c squared. Now, v in this case is 0.95 c, so we'll plug in 0.950 squared in this expression. Okay, so that works out to, if you crunch the numbers, 1.483 years. And we'll keep 3 sig figs on that and round it to 1.48. And that's the answer, but let's take a second to really think about what this implies. So according to people on Earth, the ship has been gone for 4.75 years. But according to people on the ship, they've only been gone for 1.48 years. Now, that's not just some sort of illusion. This actually is the case. This is how it works. And it will affect how people age. So, in other words, people on the ship are aging more slowly than people on Earth. And so, let's say that we have two twins, people that have the same exact age, but one of them leaves and goes on this ship, and the other twin stays on Earth. The twin that left on the ship, again, is aging more slowly. So if the ship returns and the two twins meet back up, now they have different ages. The one that stayed on Earth is now older than the twin that went on the ship. Okay? That's one of the weird consequences of time dilation. And so I just briefly want to talk about the unit of light years, which you may have heard of before. A light year is actually a unit of length, and it's defined as the distance that light travels in 1 year. So if that's the definition of the light year, let's think about the fact that distance is just equal to speed times time. So the distance that light travels in 1 year would be the speed of light times the time, which of course is 1 year. So one way we can write this is the speed is equal to c, and the time is equal to 1 year. So sometimes we see a light year written in this way, 1c times years. Now, you can also define things like light minutes and light seconds, light hours in the same way. So a light minute would be the distance that light travels in 1 minute, and a light second would be the distance that light travels in 1 second. So those are defined in a similar way. And just to give you a sense of scale, like how big is a light year? Well, the distance from our solar system to the nearest star system, which is Alpha Centauri, is 4.37 light years. Okay, so a light year is approximately the distance between stars in our galaxy, or more like a couple light years. So with that said, let's do a little practice question here. How long does it take for a ship traveling at 0.1 c to travel a distance of 2 light years? So pause the video for a second, try to work this out, and then we'll go through it together. So this is actually pretty simple. We're going to start with the idea that distance is equal to speed times time, so d is equal to v times t. And in this case, we're interested in solving for t. So t would be d over v, so distance over speed. And here's how we're going to handle the distance. It's 2 light years, but remember, I can write this as 2c times year. And on the bottom, I have the speed, which is 0.1 c. So notice I can cancel out those units of c on the top and bottom, and I'm just left with years. So 2 divided by 0.1 is 20. So if we need to travel 2 light years, and we're traveling at a speed of 0.1 c, that's going to take 20 years. That's the idea. So we talked a lot about time dilation. Now we're going to move on to a different relativistic effect called length contraction. And length contraction is just as weird and counterintuitive as time dilation. So let's get into it. So to sort of build up the picture of what length contraction is, let's do a little thought experiment. So in this thought experiment, we have two signposts, A and B, which are placed on the ground. And we have a ship that comes by, traveling to the right and moving parallel to the ground. So we have two frames of reference that we can analyze this situation in. We have the Earth frame of reference, that's just a set of coordinates that's fixed to the Earth. And then we have the ship frame of reference, which is, of course, moving with the ship. So let's let L0 be the distance between the signs as measured in Earth's frame of reference. So to start off, we're going to just analyze the situation in Earth's frame of reference. And then we'll say V is the speed of the ship measured, again, relative to Earth's frame of reference. So here's what the motion looks like as seen in Earth's frame of reference. Okay, so the ship comes by, passes over sign A, and then it passes over sign B. So the time when it passes over sign A is TA. The time when it passes over sign B is TB. And again, this is all measured in Earth's frame of reference. So delta T, the time interval, the amount of time that passes between those two events, is TB minus TA. And notice that this is not the proper time because these two events don't happen at the same location. They happen at two different locations, at least in Earth's frame of reference. So we'll remember that speed is equal to distance over time. That's the definition. So V is equal to L naught. That's the distance between the signs measured in Earth's frame of reference, divided by delta T, the time that passes in Earth's frame of reference. So now let's analyze the same exact situation using the ship's frame of reference. So what will things look like from the perspective of an observer in the ship? Well, the first thing to note is that from the ship's frame of reference, the signs appear to be moving to the left at speed V. So let's take a look at an animation to really see what this looks like. So if you're riding in the ship, this is what you'll see. You'll see the signs A and B moving to the left at speed V. So the time that it takes to pass between the signs in the ship's frame of reference is actually the proper time because we have these two events, the ship passing over sign A and the ship passing over sign B. In the ship's frame of reference, those two events happen at the same location. Let's take a look. In other words, when the signs pass underneath the ship, those events happen just at the origin of the ship's coordinate system. They happen at the same location. Therefore, the time in between those two events is the proper time, delta T naught. So let's also let L be the distance between the signs that would be measured in the ship's frame. Okay, so distance, of course, is equal to speed times time. That's just the definition here. And the distance in question is L. Okay, that's the distance between the signs. The speed that the signs are moving past the ship is V, and then the time interval is delta T naught. So from before, we saw that V is equal to L naught divided by delta T, so we can actually sub that in for V right here. And that gives us L equals L naught times delta T naught over delta T. But let's remember how time dilation works. The equation for time dilation says that delta T is equal to gamma times delta T naught. In other words, if we plug in down here gamma times delta T naught, we'll see that the delta T naught factors cancel, and L is just equal to L naught divided by gamma. Now take a second to really think about what this equation is saying. L, that's the distance between the two signs as measured in the ship's frame of reference, and L naught, that same distance as measured in Earth's frame of reference, are not the same thing. So not only do we have time dilation, which is the idea that these two frames of reference won't agree on how much time has elapsed between two events, but there's also something called length contraction going on here, where the two frames of reference don't agree on the distance between things or the length of objects. So that's the idea behind length contraction. Different observers will not necessarily agree on the distance between two objects or even the length of a single object. The relationship there is L is equal to L naught divided by gamma. And let's remember what gamma is. Gamma is 1 over the square root of 1 minus v squared over c squared. So we can say L is equal to L naught times the square root of 1 minus v squared over c squared. Now, there's a difference between L and L naught. These aren't just arbitrary labels. We have to keep track of which one is L, which one is L naught. L naught is what we call the proper length. That would be the length of an object as measured in a frame of reference where the object is at rest. So if we think about the example we just did with the two signposts, L naught was the distance between the two signs in Earth's frame of reference where the signs are at rest. Whereas L was the distance between the two signs in the ship's frame of reference, where in the ship's frame of reference, the signs are actually moving. They're not at rest. So L is the length of an object as measured in a frame of reference where the object is moving. Okay, so if we take a look at this equation, V over C is going to be a number between 0 and 1. Okay, you can be moving at 0 speed, and then the speed of light c is the absolute upper limit for how fast you can be moving. So this is a number between 0 and 1. And then we're taking 1 minus that, and then taking the square root. So this entire factor in front of L naught is always going to be something less than 1, which means L is always going to be smaller than L naught, okay? So the greatest length for an object that we can possibly measure is the proper length. In other words, L is always going to be less than L naught. And that means if we look at an object in a frame of reference where it's at rest, we measure its proper length. If we look at an object in a frame of reference where we see the object moving, then we measure what's called a contracted length, something that's less than L naught. That's why this whole effect is called length contraction. Now, one really important thing to note here is that length contraction only happens along the direction of motion. So if you see a spaceship flying past you very fast, close to the speed of light, you'll see the length of that spaceship be contracted in the direction it's moving in, but perpendicular to that direction, the length is not contracted at all. It only happens along the direction of motion. So let's do an example. As measured from Earth's frame of reference, the distance between Earth and Neptune is 2.7 billion miles. A spaceship is traveling in a straight line from Earth to Neptune at a constant speed of 0.99 c. The question we want to answer here is, what is the distance between Earth and Neptune in the ship's frame of reference? And then how long does it take to complete the journey from Earth to Neptune in each one of these frames of reference? We're going to need to know a few things. The speed of light is 3 times 10 to the 8 meters per second, and 1 mile is equivalent to 1,609 meters. In this problem, we're going to neglect the relative motion of the planets. So of course, Earth and Neptune are in fact moving relative to one another, but we're going to ignore that just to make the problem a little bit simpler. So let's work this out. Okay, so let's label the frames of reference on the diagram. First, we have Earth's frame, and then we have the ship's frame. So that would be a set of coordinates that is moving with the ship. Now, the proper length in this problem, that is the distance between Earth and Neptune, is seen in Earth's frame because that's the frame of reference where the planets are at rest. Okay, and that proper length, L naught, is 2.7 billion miles. And a billion is the same as 10 to the 9, so that would be 2.7 times 10 to the 9 miles. We're going to see a contracted length, on the other hand, a shorter length, in other words, is seen in the ship's frame. And of course, the ship is going to see the Earth and Neptune moving, so that wouldn't be the proper length. Okay, so we don't know what L is. But according to the equation we derived for length contraction, L is just equal to L naught divided by gamma, or L naught times the square root of 1 minus v squared over c squared. So remember, gamma is 1 over the square root of 1 minus v squared over c squared. So if you do 1 over gamma, you put the square root on top. Okay. So we have L naught, which is 2.7 times 10 to the 9 miles, multiplying the square root of 1 minus v squared over c squared, where v is equal to 0.99c, so we have 0.99 squared here. The factors of c will drop out. Okay, so if you calculate this, it turns out to be 3.81 times 10 to the 8 miles, which we can write as 381 times 10 to the 6. And actually, we're keeping 2 sig figs on this. So that's about 380 million miles. So it's a much shorter distance from the perspective of the ship. Because the ship is moving so fast relative to these planets, it sees the distance between the planets contracted by a lot. Instead of 2.7 billion miles being the distance it needs to cover, now it's only 380 million miles. Okay, that's the effect of length contraction. Now, if we want to figure out how much time has passed in each frame, well, there are a number of different ways we can do this. We could use the formulas for time dilation that we derived earlier, or we can do this. Just remember that speed is equal to distance over time, which means time is equal to distance over speed. So the reason in these two frames of reference we get two different times is because we have two different distances that are measured. In the ship's frame of reference, the length is contracted, so the distance is smaller. It takes a smaller amount of time as a result. So let's work that out. In Earth's frame, the time, let's call it delta t, would be the distance between the planets, which is 2.7 billion miles. So 2.7 times 10 to the 9 miles. But if we want to convert that to meters, we'd just multiply by 1,609 meters. So that's the distance in Earth's frame measured in meters. We'll divide that by the speed, Well, the ship is moving at 0.99 c, so 0.99 times 3 times 10 to the 8 meters per second. So this gives us a time in seconds. Units of meters drop out. And it turns out to be 14,627 seconds. But we're only keeping 2 sig figs on that. Let's convert that to hours. In every 1 hour, we have 60 times 60 seconds, or 3,600 seconds. So this works out to 4.06, which will round to about 4.1 hours. So, according to observers on Earth, it takes the ship just over 4 hours to get to Neptune. But if we look at the same time interval delta t in the ship's frame, we're going to get something else. Because now, when we do delta t is equal to distance over speed, the distance between the planets in the ship's frame is 3.81 times 10 to the 8 miles. That's what we found over here. And so we'll take that and multiply by 1,609 to get it in meters. And according to the ship, the planets will be moving past at 0.99 c. 0.99 times 3 times 10 to the 8 meters per second, and we'll cancel out meters and be left with the time in seconds. So that time will be 2,064 seconds, a much, much shorter time. And if we convert that to hours, where we have 3,600 seconds in every 1 hour, it works out to 0.573 hours, or about 0.57 hours. Okay, so again, according to observers on Earth, they're going to see it take 4.1 hours for the ship to get from Earth to Neptune. But if you're riding on the ship, it seems like it only takes a little over half an hour. Completely different times. We could have also solved for this 0.57 hours if we use the formula for time dilation, but again, this way works also. Okay, so here's another example for you guys to try out. When you stand at rest next to your framed picture of Albert Einstein, you measure its dimensions as L naught, so the length over here is 35 centimeters, and H naught, the height, is 75 centimeters. So of course, this would be the proper length and the proper height because that's what we measure when we see the picture at rest. So now let's suppose you are running to the right at 75% of the speed of light. So you're running this way at 75% of the speed of light. What dimensions do you measure now? So what do you measure as the length and the height of the picture in this case? So pause the video, try to work it out, and then we'll go through it together. Okay, so the first thing to realize is that H, the height that we'll measure when we're running at 75% of the speed of light relative to the picture, is the same as H naught, the height that we'll measure if we're just standing still. And the reason for that is length is only contracted along the direction of motion. And there's no length contraction perpendicular to that. On the other hand, when we consider L, that is going to be contracted. L is equal to L naught divided by gamma, which, as we saw earlier, is L naught times the square root of 1 minus v squared over c squared, where L naught is 35 centimeters and then we have the square root of 1 minus. So if we're at 75% of the speed of light, let's just write this down, then v is equal to 0.75 times c, which means we have 1 minus 0.75 squared under the square root here, which if you crunch the numbers comes out to 23.15 centimeters, or 23 centimeters when we keep 2 sig figs. So the dimensions you see are L by H, 23 centimeters long, and 75 centimeters high. So that 75 centimeters hasn't changed. So, to summarize what we found, in Earth's frame of reference, we're going to see the picture stationary. It's not going to be moving in that frame of reference. So, for each dimension, we have the proper length. So, 35 centimeters is the length here, 75 centimeters is the height here. Now, if we look at the running person's frame, the running person is going to see the picture moving to the left at 0.75 c. And so the length of the picture is going to be contracted. Now it's 23 centimeters on this side, but the height is unchanged because length contraction only happens along the direction of motion. So perpendicular to the direction of motion, there is no length contraction. So now the dimensions are 23 by 75 centimeters. And that means in the running person's frame of reference, the picture looks warped. It looks like it's being squished horizontally. And the effect of that is Albert Einstein looks skinnier than he does in this picture. Okay? All right, so let's continue on with this discussion of length contraction. And I'm going to outline a scenario for you that appears to be a paradox. Okay, it appears to indicate that there's something deeply wrong with the theory of relativity at first glance, but then we'll see how to resolve the paradox when we look at it a little bit more deeply. So a train moving at 0.950 c relative to the ground goes into a tunnel. In Earth's frame of reference, the train has a length of 55 meters, and the tunnel has a length of 55 meters as well. Okay, so we see the train in Earth's frame of reference as being 55 meters long. We see the tunnel as also being 55 meters long. In Earth's frame of reference, the tunnel is not moving, but of course the train is moving to the right at that speed, 0.950 c. So, this is what the motion looks like. Let's see it again. Okay, so for now, the takeaway point is that if we're observing the motion from Earth's frame of reference, so if we take the perspective of someone that's just standing on the Earth and watching the train go by, that observer is going to see the train disappear inside of the tunnel, at least for a brief moment in time. Because the train and the tunnel have the same length, at some point the train will be completely inside of the tunnel and you won't be able to see it. Okay, that will be the case in Earth's frame of reference. So that all seems reasonable so far, but problems arise when we start to think about what this all looks like in the train's frame of reference. So the first thing to note is that the 55-meter length of the train is what we will measure in Earth's frame of reference, where we see the train moving. In the train's frame of reference, where the train is at rest, we see actually a much larger length. We see 176 meters, which is the proper length of the train, not the contracted length that we saw earlier. So we're going to work this out in a second. Why is it 176? But notice that in addition to that, the length of the tunnel is now contracted. So the 55-meter length of the tunnel that we saw earlier was the proper length, which is what you observe when the tunnel is at rest. In the train's frame of reference, the tunnel is actually moving. It's moving to the left at 0.950 c. So we see its length get contracted along that direction of motion. And if we calculate that length, it's 17.2 meters. So before we go any further, let's just calculate those distances so we know why it's 176 meters for the train and 17.2 meters for the tunnel. Okay, so first, let's consider what we know about the train. So L is 55 meters. What do we mean by that? This is the contracted length, which is the length we see in Earth's frame of reference, because that's the length we see in a frame of reference where the train is actually moving. Okay, L naught, we don't know what that is. We'll calculate it, but this would be the proper length in the train's frame of reference. So the proper length is what you see in a frame of reference where the object is not moving, which would, of course, be the train's frame of reference. So for length contraction, we have L equals L naught divided by gamma, which means L naught, if we want to know the proper length, is gamma times L. And gamma is, of course, 1 over the square root of 1 minus v squared over c squared. So again, the contracted length L is 55 meters, and we're dividing that by the square root of 1 minus, the speed is 0.95 c. So we have 0.950 squared right there. And again, if you crunch these numbers, you get 176 meters. So the proper length of the train is actually 176 meters. We only see it as 55 meters in Earth's frame because the train is moving in that frame. Okay, what about for the tunnel? Well, L naught is 55.0 meters. Okay, this is the proper length. So this is the length of the tunnel you would measure in a frame of reference where the tunnel is at rest, which is Earth's frame. And so what we don't know is the contracted length, L, and that's what we'd see in the train's frame. Because in the train's frame of reference, the tunnel is moving. Okay, so L equals L naught divided by gamma. But the difference between the calculation we just did and this calculation is we're trying to find L. We're not trying to find L naught. So again, gamma is 1 over the square root of 1 minus v squared over c squared. So we have 1 over that. So we have L naught times square root 1 minus v squared over c squared. And if we plug in the numbers, we have 55 meters, square root 1 minus 0.95 squared. And that's where the 17.2 meters comes from. Okay, so the length of the train is 176 meters. The length of the tunnel is 17.2 meters, as seen in the train's frame of reference. In the train's frame of reference, we see the tunnel moving to the left at 0.95 c. So let's look at an animation of that motion. Okay, so the train sees the tunnel moving to the left, and sort of moving over the train like this. Now, immediately, there's a problem, because according to observers in the train's frame of reference, the train is never completely inside of the tunnel. It's just impossible. The train is way too long to be completely inside of the tunnel. But in Earth's frame of reference, the train was completely inside of the tunnel. How is it that in one frame of reference, the train is completely inside of the tunnel, and in another frame of reference, the train never is completely inside of the tunnel? That kind of looks like a paradox, okay? So we need to explain how that can be possible. So to resolve this paradox, it turns out that what we need to do is rethink our concept of what's called simultaneity. Simultaneity is the idea that two events happen at the same time. They're simultaneous. So in this scenario involving the train and the tunnel, we have two different events to think about. Event A is the front of the train passes the front of the tunnel. And event B is the back of the train passes the back of the tunnel. Now, in the Earth frame, these two events are simultaneous. They happen at the same time. So the front of the train is lined up with the front of the tunnel at the exact same time as the back of the train is lined up with the back of the tunnel. Those two things happen at the same time in Earth's frame. Now, in the train's frame, those two events are not simultaneous. They don't actually happen at the same time. In the train's frame of reference, the front of the train passing the front of the tunnel happens first. And then later on, the back of the train lines up with the back of the tunnel. They're not simultaneous events. Event A happens before event B. So I think most of us have an intuition for simultaneity, which says, look, if two events are simultaneous in one frame of reference, then they must also be simultaneous in another frame of reference. So if I see two things happening at the same time, then you will also see those two things happening at the same time. But it turns out that's just not true. Simultaneity is actually not absolute. Whether or not two events happen at the same time depends on your frame of reference. And that's how we resolve this paradox. It's the idea that what was a simultaneous pair of events in Earth's frame is not a simultaneous pair of events in the train's frame. And oddly enough, that can happen according to the theory of relativity. So there's another version of that length contraction paradox that basically conveys the same idea, but it's sort of told in a different way. So I just want to outline this for you real quick. So the idea is we have a snake. So here's the snake, and it's slithering along the table close to the speed of light. So from my perspective, I see a contracted length for the snake. Okay, so whatever its proper length is, I'm seeing something that's actually shorter than that because the snake is moving relative to me close to the speed of light. Okay, so while the snake is moving, okay, I'm gonna hold two knives out the exact same distance apart as the length of the snake. And then just when the snake comes by, I'm gonna drop those knives down so that the snake just barely fits in between the knives and then lift them right back up. Okay, so because the snake fit in between the two knives, there's no problem. I didn't actually cut the snake. The snake is unharmed. So now let's think about what this all looks like from the snake's perspective. So in the snake's frame of reference, the snake is going to say, I'm not moving. Okay, the snake is not moving in its own frame of reference, so the length of the snake is the proper length, which is bigger than what I'm measuring in my frame of reference. And then furthermore, the snake is going to say that I'm actually moving at close to the speed of light relative to it, so the distance between my knives is going to get contracted. Okay? So the distance between the knives in the snake's frame of reference is smaller than in my frame of reference due to length contraction. So the point is, in the snake's frame of reference, the distance between my knives is now smaller than the length of the snake. So when I bring the knives down, there's no way for the snake to actually fit in between the knives anymore. But that seems like a paradox, because in my frame of reference, I never cut the snake, because the snake was able to fit in between my knives. But in the snake's frame of reference, it seems like maybe I am cutting the snake, because it's not able to fit in between the two knives anymore. So we resolve this paradox by again going to the idea of simultaneity. In my frame of reference, the knives came down at the exact same time. Those were simultaneous events. In the snake's frame of reference, those are not simultaneous events. In fact, in the snake's frame of reference, here's what happens. This knife comes down first, misses the snake's head. Then the snake moves out of the way, and the next knife comes down after that, so I miss the tail. Again, this relies on the idea that the knives coming down don't happen at the same time in the snake's frame of reference. That's how the snake doesn't get cut. Okay, so we've covered two really important relativistic effects, which are length contraction and time dilation. So what I want to cover next is the Lorentz transformations. So in a nutshell, the Lorentz transformations give you a way of going between two different frames of reference. In other words, if I know how a certain motion looks like in one frame of reference, what does it look like in a different frame of reference? That's what the Lorentz transformations allow you to do. Now, part of the picture that we're going to develop with these Lorentz transformations involves what's called four-dimensional or 4D spacetime. So what's this all about? Well, in Newtonian physics, we use a set of three-dimensional coordinates to tell us the position of an object, right? X, Y, and Z are the three-dimensional coordinates that we use to say where an object is located, to say what its position is. In relativity, we do this slightly differently. We also include time as a coordinate. So now we have four numbers. We have a four-dimensional object, which we call the 4D space-time coordinates for an event. So in other words, we have X, we have Y, we have Z, just like before, but now we also have a time coordinate, so it's now a four-dimensional object. Now, what we mean by an event is that there is a position, there's a location where something happens, but also when something happens is part of the event. So where and when together constitute an event. So here's an example. Let's say that you have a meeting on the roof of the building on the corner of 6th Street and Grand Avenue at 6 p.m. Okay, that's an event. There's a meeting, you have to be at a certain location and you have to be there at a certain time. So the X and the Y coordinates, let's say those are the horizontal coordinates, that would tell you where on the street are you supposed to go. So you go to the intersection of 6th Street and Grand Avenue. That would be given by your XY coordinates. Your Z coordinate would indicate your height. So that would say we're going to go all the way up to the roof of the building. That would be the Z coordinate. And then the T coordinate tells us just what time to be there, 6 p.m. Okay, so that's just an example of an event. We have X, Y, Z, and T to specify an event in four-dimensional space-time. So we're combining space with time in this way of doing things. Okay, so next, let's talk about coordinate transformations. What I mean by this is if I have a set of coordinates X, Y, Z, and also T in one frame of reference, what will those coordinates be if I transform to a different frame of reference? So this is the basic setup. We have frame S prime, where the axes are labeled X prime and Y prime, and then the Z axis would be coming out of the page towards us. The origin of that coordinate system is shown right here as O prime. That frame of reference is moving to the right at speed V relative to this frame, which is frame S. The axes here are labeled X and Y, and then the origin is O. So this one again is moving at speed V relative to frame S. Now, the origins of the two frames of reference at some point are going to coincide. So let's call the moment they coincide t equals 0. In other words, for each frame of reference, we're going to sort of start the clock, start measuring time at the moment when the two frames have their origins coincide. So here's a picture of what that looks like. So we have frame S prime moving at speed V along the X direction relative to frame S. And right when their origins meet, right when they coincide, that's how we define t is equal to 0. Okay? So if we have a particular point that we're looking at, let's call it point P, we want to be able to go from the coordinates of that point in frame S prime to the coordinates in frame S. We're going to transform the coordinates between the two frames. And for now, we're going to do this ignoring relativity. We're going to do this in the old-fashioned way. Before we knew anything about relativity, this is the way Galileo worked it out. This is called the Galilean Transformation. Okay, so first of all, we'll note that there's a distance between frame S and frame S prime. And that distance is just the speed that the frame is moving with times the time that has elapsed. So it would be v times the time, v times t prime. Okay, now this distance between the origin of the coordinate system S prime and the point along the x-axis is what we call x prime, and that's shown here. And then x is the distance between the origin and the point along the x-axis in frame S, okay? Now, just by looking at those three distances, we can see that x is equal to x prime plus v times t prime. Okay, so this distance is just this plus this added together. On the other hand, if we look at the y coordinates, well, y prime is the same as y. They actually agree in terms of that coordinate because there's no motion along the y direction. And same with z. They'll agree on the z coordinates, so z is equal to z prime. And then this is a really important point. If we're not accounting for relativistic effects, then the time coordinates will also agree. There's no disagreement about time. There's no time dilation. So t is just equal to t prime. Now, these transformations, again, allow you to go from the coordinates in the primed frame of reference, so we know all the primed variables. We can calculate the unprimed variables, so we can switch between frames of reference. But these only work in the non-relativistic regime. So we're assuming that the speed v is a lot less than the speed of light. As long as that's the case, this works perfectly well. We can ignore relativistic effects whenever the speeds are very small compared to the speed of light. But keep in mind, this all breaks down. This doesn't actually work when the speeds start to approach the speed of light. Okay, so we can take this one step further and see how we can transform not only the positions, x, y, z, and the time, but also the velocities between two frames of reference. So here's what we're looking at. We have a particle, let's call that particle P, moving with velocity u prime, and the components are ux prime, uy prime, and uz prime, as seen in frame S prime. So this is the velocity measured in this frame. What we want to know is, what is the velocity in frame S? So if I know the velocity in one frame, what's the velocity in the other frame? How do I transform velocities between two frames of reference? So let's take this component by component. Ux, that's the velocity of this particle along the x direction as seen in frame S, because there's no prime, we're talking about frame S. Well, the definition of the x velocity is dx dt, the derivative of x with respect to time. So we're taking the derivative with respect to time of x, but we know from our Galilean transformation that x is equal to x prime plus v times t prime. So how do I evaluate this derivative? Well, when we evaluate derivatives, remember, in the Galilean transformations, t and t prime are the same thing. So we can treat them as the same thing in this case. So I'll have two terms. I'll have dx prime dt, and then I'll have the derivative of the second term. V is a constant, and then we're taking the derivative of t with respect to t, which gives you 1. So we just are left with the constant v in that case. Okay, so we have dx prime dt, which, by the way, is just ux prime. That's just the velocity along the x-axis in the primed frame, plus v. That's how this one works out. Let's do the y direction. uy is equal to dy dt. So we're taking the derivative with respect to time of y, but that's the same as y prime. Y and y prime are the same. So we just get uy prime. In other words, since there's no motion between the frames along the y direction, the velocities we see along the y direction in the two frames will be the same. Uy is equal to uy prime. And then uz, let's do that. That's dz dt, which is the derivative with respect to time of z, which is the same as z prime. So this gives us uz prime. Again, in the z direction, the velocities are identical because there's no motion between the frames along the z direction. So that's how we transform velocities according to Galileo. This is pre-relativity. This is what you would do. And what it basically boils down to is adding velocities, right? Just like this. So in Galilean relativity, the velocities simply add. Now, you can probably imagine if we account for relativistic effects and we actually use the theory of relativity to solve this problem, it's not going to be so simple, okay? So next, let's see how this works in relativity. In the relativistic regime, when V is close to C, where we actually have to account for relativistic effects, the Galilean transformations that I showed you do not work. They break down. Instead, you need to use what are called the Lorentz transformations in order to switch between frames. Now here are the Lorentz transformations. Okay, same setup as before. We have frame S prime moving at speed v with respect to frame S, and we're going to just say that the motion is along the x-axis. So what I want to do is take the coordinates x prime, y prime, z prime, and then also t prime for the time, and transform that to frame S. So I want to know what the coordinates x, y, z, and t are. I want to go from one frame to the other. This is how it works. I'm not going to show you the derivation in this video, although I have a derivation written out and I'll make it available on Canvas for how we actually get all of this, but it's a bit lengthy, so I'm going to leave it out of the video. Here's what it is. X is equal to gamma times the quantity x prime plus v times t prime. Y is equal to y prime. Z is equal to z prime. So we agree on those coordinates where there's no motion. But t is equal to gamma times t prime plus v times x prime divided by c squared. Okay, so notice a few things about the Lorentz transformations. The two frames of reference no longer agree on the time coordinate. T is not the same as t prime. In relativity, there's not an agreement about the passage of time. Also, notice how the space and the time coordinates are getting mixed up together. That's something you'll see when you dive deeper into relativity, is that space and time coordinates tend to mix together in your equations. Okay, so that's the Lorentz transformation. That's what it says. So next, we're going to use those Lorentz transformations to figure out how do I actually take a velocity in one frame of reference and transform that velocity to another frame of reference, okay? How do we actually do this properly using the relativistic equations, the Lorentz transformations? So the problem we're trying to solve is the same as before. We have frame S prime, and we have a particle moving with velocity u prime as seen in that frame. Now, that frame S prime is moving itself at speed v with respect to frame S along the x direction. So what is the velocity of that particle as seen in frame S? That's what we're going to work out. Okay, so I've copied down the Lorentz transformations. We've seen these before, so I just want to put them here on the page because we'll be referring to these as we go. But what we're going to look at are velocities. In particular, let's start with ux. So that would be the velocity of this particle in frame S, the unprimed frame. So by definition, velocity along the x-axis is dx dt, of course. And we can use the Lorentz transformation to substitute x. This is the derivative with respect to time of x, which is, according to the Lorentz transformation right here, that's gamma times x prime plus v times t prime. So we need to take the derivative with respect to t of that whole quantity. So we have gamma is a constant, so we'll bring it to the front outside of the derivative. And then we'll have dx prime dt for the first term. And then we'll have two constants, gamma and v, which we can pull out in the second term. And then we'll have dt prime dt. Now here's the thing to remember, t and t prime are no longer the same thing when we're using the Lorentz transformation. So we have to be very, very careful about how we have to evaluate this derivative. Okay, so first, let's expand out the first term. We have gamma, and then we have dx prime dt. So I'm going to use the chain rule to expand that derivative out. This would be dx prime dt prime times dt prime dt. Okay, so that's how we take this derivative here and expand it out using the chain rule. Okay, the second one, I'll just leave it alone for now. It's gamma times v times dt prime dt. So to write this in a more compact way, we have a common factor of gamma that we can pull out in both terms. And then we also have dt prime dt in both terms. So then in the parentheses, we'll have dx prime dt prime plus v in the parentheses. Okay, but what we should notice here is that the x velocity in frame S prime is ux prime, and that's equal to dx prime dt prime. That's the velocity we would see along the x-axis in this frame. Well, that's actually the first term in the parentheses. So what we have over here is gamma times dt prime dt times ux prime plus v. So that's how we would transform the x velocity. But we're not quite done yet because we have to figure out what is this thing? What is dt prime dt? And so to work out that derivative, we're going to use the Lorentz transformation for time. And so what I want to do is take that equation and flip it around so that we solve for t prime. So t prime equals something. Well, first, divide by gamma on both sides. So you'll have t divided by gamma, and then we'll simply subtract this term. So we have minus v times x prime over c squared. Okay, so that's t prime according to our Lorentz transformation. And what we want to do is take the derivative of t prime with respect to t. We need to know that in order to complete our work over here. So, well, we have two terms. The first one is t over gamma. The derivative of t with respect to t is 1, so that's just 1 over gamma. Gamma is a constant. Now for the other term, we have minus v over c squared. Those are constants, but x prime is not a constant. So we have dx prime dt when we take that derivative. Okay, so next, let's rewrite this. Dt prime divided by t dt is equal to 1 over gamma minus v over c squared. What I'm going to do next is apply the chain rule once again. So if I have dx prime dt, that's the same as dx prime dt prime times dt prime dt. That's the chain rule. Okay, well, a few things to note about that. The first is, so let's leave the left side alone. Let's leave the first term alone, and then we have minus v over c squared. You see this term right here, dx prime dt prime? Well, that's the same as ux prime, as we said earlier. So that's ux prime, and then we're multiplying dt prime dt. So what I'll do is, since I'm trying to solve for dt prime dt, I have to sort of combine the two terms that have that in them. So let's add this term to both sides and pull out the dt prime dt factor. So I'll have a factor of 1 multiplying that from this term, and then plus v times ux prime divided by c squared from this term. And then that would equal 1 over gamma. So therefore, dt prime dt would equal 1 over gamma times 1 plus v times ux prime divided by c squared. Okay, so here, let me point out what we had earlier. So let me just circle this. We had ux equals gamma times dt prime dt, which we just worked out, times ux prime plus v. So let me copy that down over here. Ux is equal to gamma times dt prime dt times ux prime plus v. But now I'm going to sub this in for that dt prime dt derivative. So we have gamma times 1 over gamma, 1 plus v ux prime over c squared times ux prime plus v. So we're basically done, but to clean this up, ux is equal to ux prime plus v on top divided by, gammas cancel, 1 plus v times ux prime over c squared on the bottom. So the way we transform the velocity in relativistic terms is not quite as simple, okay? We're not simply adding the velocities. We have this extra factor in the denominator that we have to account for. Okay, so that is our first result. That's how we transform the x velocity. How do we transform the y velocity? Uy. Well, that would be equal to dy by dt, right? And according to our Lorentz transformations, y and y prime are the same thing. So this derivative can be written as dy prime dt. Okay, now let's chain rule that guy. This is dy prime dt prime times dt prime dt like this. Okay, that's the chain rule. Now the y velocity in frame s prime would be what we call uy prime, which would be dy prime dt prime. Well, that's the first term in our chain rule. The second term in our chain rule is the derivative of t prime with respect to t, which we spent a whole bunch of time working out just a second ago. So all we're doing is combining those expressions, okay? So uy is equal to dy prime dt prime, which is uy prime. And then we multiply that by 1 over gamma times 1 plus v times ux prime over c squared. We worked that out before. But remember that gamma is equal to 1 over the square root of 1 minus v squared over c squared. So if we substitute that in, we can write this as uy prime times the square root of 1 minus v squared over c squared divided by, so that's the 1 over gamma right there, divided by 1 plus v times ux prime over c squared. That's how we transform the y velocity. Okay? And then if we do the z velocity real quick, uz, that's dz dt. Z is the same thing as z prime, because the motion between the frames is only in the x direction. So this gives us dz prime dt. Those are the same thing. And then if we chain rule this like before, we have dz prime dt prime times dt prime dt. Now, just like before, dz prime dt prime, the first term is uz prime. That's the z velocity in the primed frame of reference. But we're multiplying that by this time thing, which we worked out before, which is 1 divided by gamma times 1 plus v times ux prime over c squared. So hopefully you can see that this works out pretty much the same as the y transformation, which will give us uz prime square root 1 minus v squared over c squared divided by 1 plus v times ux prime over c squared. Okay, so we worked out all the velocity transformations. We worked it out for x, we worked it out for y, we worked it out for z. So now we can do fully relativistic velocity transformations. And again, it's a little bit more complicated than in the non-relativistic limit. But I want to do one more thing with this. I want to show you that in the non-relativistic limit, where v is much, much less than c. That's what it means to be non-relativistic. The speed is much less than the speed of light. Well, another way we could say this is v divided by c is much, much less than 1. V divided by c is a really small number in the non-relativistic limit, okay? So our velocity transformation for x is ux equals ux prime plus v divided by 1 plus v times ux prime divided by c squared. Or I could write this, instead of c squared, it's just c times c. So notice how we have this v over c in the expression right here. And as we said, in the non-relativistic limit, where speeds are very slow, v over c is a really small number. So basically what we have is ux prime plus v divided by 1 plus something that's small number. And of course, we can approximate that as just ux prime plus v. And that is our Galilean transformation. So the relativistic equations boil down to the plain old Galilean equations in the limit where we're in the non-relativistic regime. Okay, let's do another one. Uy, that's equal to uy prime times the square root of 1 minus v squared over c squared, which I'll write as v over c squared like this, over 1 plus that same quantity as before, v times ux prime divided by c squared, which I'll write as c times c. So again, we have this v over c right here. That's a very small number. And we also have it right here on top. So what we should think of this is we have uy prime times square root 1 minus a very small number squared divided by 1 plus a small number. So approximately the thing in the square root is just 1, and the thing in the denominator is also just 1. So we get that the y velocity in the two frames of reference are approximately the same. Again, that's just the Galilean transformation. Okay, lastly, let's do z. uz is equal to uz prime times the square root of 1 minus v squared over c squared divided by 1 plus v times ux prime over c squared. So this is the same exact scenario as for the y direction. What we have is uz prime times the square root of 1 minus a very small number squared divided by 1 plus a very small number. And of course, that's approximately just equal to uz prime. Again, it's really important to show that our relativistic equations boil down to the plain old equations of classical physics when we're in the non-relativistic limit. This is called the correspondence principle, okay? And it applies to everything we've seen up until this point. It applies to the velocity transformations as well. So here's a summary of what we found. We found that ux, the velocity along the x-axis, which is dx dt, is given by, well, the derivative with respect to time of gamma times x prime plus v times t prime. So this is x according to our Lorentz transformation. But the reason this was a tricky derivative to evaluate is that t that you see here and t prime that you see here are not the same thing. They're related by this Lorentz transformation. So after doing some of the work, we got ux is equal to ux prime plus v divided by 1 plus ux prime times v over c squared. So that's how we transform the x velocity from frame s prime to frame s. Now for the y velocity, we have uy is equal to dy dt, as we said. And then y and y prime are the same thing in our Lorentz transformation. But what makes this tricky, once again, is t and t prime are not the same. So this took a little bit of extra work, but when we got it, we found that uy is equal to uy prime square root 1 minus v squared over c squared divided by 1 plus ux prime times v over c squared. So that's how we go from the y velocity in the primed frame to the y velocity in the unprimed frame. And then the same thing for z. This basically works the same way as for y because there's no motion between the frames along this direction. And so what we got is uz is equal to uz prime times the square root 1 minus v squared over c squared over 1 plus ux prime times v over c squared. That's how we do relativistic velocity addition. It's a little bit more complicated. So let's take a look at an example where we actually get to use the relativistic velocity transformations. So Bob is in a spaceship, which is traveling at speed v equals 0.900 c relative to the Earth. And Bob throws a ball, which moves at a speed 0.500 c, which is moving along the positive y-axis from his perspective. So Alice is observing all of this motion from the Earth. So the question is, what is the speed of the ball in Alice's frame of reference? And also, what is the direction of the ball's motion? We're going to give that as an angle relative to the x-axis in Alice's frame of reference. So of course, in Bob's frame of reference, the ball is just moving along the y-axis. But in Alice's frame of reference, she's going to see the ball moving at some angle We're going to try to figure out what that is, and again, also how fast the ball is moving from Alice's perspective. So let's work this out. Okay, so we'll start with a little bit about the notation here. Whenever I write a variable with a prime on it, that will refer to Bob's frame of reference. So the primed frame is Bob's frame, and the unprimed frame, so when you see variables without a little prime on it, that's going to refer to anything as seen in Alice's frame of reference. Okay, so what are we given here? What do we know? Well, one thing that we're given is v. That would be the speed, the relative speed of the two frames, 0.900 c. So relative speed of the two frames. We also are given uy prime. So in other words, in Bob's frame of reference, we see the ball moving along the y-axis at 0.500 c, and it's not moving along the x-axis at all. It's just moving straight up from Bob's frame of reference. So ux prime would be 0. Remember, we're using the primes here. That's the velocity of the ball. That's the object we're talking about here in Bob's frame. So what we're trying to do is translate those velocities, ux prime and uy prime, into ux and uy, which is, of course, Alice's frame of reference. So we know that for ux, that's equal to ux prime plus v divided by 1 plus ux prime times v divided by c squared. So that's what we derived earlier. So we can actually just plug in what we know. Ux prime is 0. Remember, in Bob's frame, the ball is not moving on the x-axis, but v is 0.900 c. So we add that on the top, and then on the bottom we have 1 plus, well, ux prime is 0, so it actually doesn't matter what v and c are because we're just multiplying that by 0. So basically what we have is ux is equal to 0.900 c. So it's basically just the velocity that Alice sees the ship traveling with along the x-axis. That's how fast she's going to see the ball moving along the x-axis. Okay. Then we also have to do uy. So uy is equal to uy prime times the square root 1 minus v squared over c squared over 1 plus ux prime times v divided by c squared. Okay, so what is that equal to? Well, remember, uy prime is 0.500 c. We just said that earlier. And then we're taking that and multiplying by the square root of 1 minus v squared over c squared. So that would just be 0.900 squared. And then we're going to divide all that by the same thing we had in the denominator before, which is 1 plus ux prime times v over c squared. But remember, ux prime is 0, so that's just like having 1 in the denominator. Okay, so if you take your calculator out and you compute this, you're going to get 0.2179c. We'll keep 3 sig figs on that. So again, that's how fast Alice is going to see the ball moving along the y-axis. Okay, so what would be the speed of the ball from Alice's perspective? So remember how this works. It's just a little bit of trigonometry. So Alice sees the ball having this velocity vector u, and it has components ux and uy, which we can denote like this. So uy is along the y-axis, ux is along the x-axis, and there's some angle here. We'll call that theta. But if I want the speed or the magnitude of the velocity as seen from Alice's frame of reference, that's just the Pythagorean theorem. Remember, that's the square root of ux squared plus uy squared. And so that's going to be the square root of ux is 0.900c, square that, and then uy is 0.2179c, and we square that. So if you compute this, what you're going to get is 0.926c. That's the speed of the ball as seen by Alice. So notice it's not exceeding the speed of light c. And then if we want to get the angle, we can use the tangent function. So if we go to the triangle that we just drew over here, it's a right triangle. And tangent is just the opposite side over the adjacent side, which is uy divided by ux. So if we want theta, that would be the inverse tangent of uy divided by ux, which is, again, 0.2179c for uy divided by 0.900c for ux. And if you compute this, you get 13.6 degrees. So Bob sees the ball moving at 90 degrees to the x-axis, but Alice sees the ball moving at 13.6 degrees relative to the x-axis. That's what we found. Now, to make a very complicated set of equations a little bit simpler, let's stick to the case where all of the motion is in one dimension. Let's just stick to one-dimensional motion only. In other words, let's consider the case where everything just moves along the x-axis. So we can just completely ignore the y and the z equations. Just focus on the x equation. Well, again, the x equation says ux is equal to ux prime plus v divided by 1 plus ux prime times v over c squared. Now, I want to suggest a different type of notation we can use here, okay? It might be a little bit easier to set the equation up this way. So let's let VOA represent the velocity of some object relative to frame A. Let's let VOB be the velocity of the object relative to frame B. And then let's let VBA be the velocity of frame B relative to frame A, okay? So that way we're explicitly putting in our notation what are our frames of reference in the subscripts. So on the left side of the equation, we have the velocity as seen in frame A. That's VOA. That would be the velocity seen in the other frame. That would be VOB, plus the velocity between the two frames. That's what V represents up here. So in our new notation, we'll write that as VBA, velocity between the two frames. And then that would be divided by VOB times VBA over c squared. And how do we know that we set this up right? Well, the subscript on the left side is O on this side of the equation. It also appears on the left side here. The subscript on the right side of this side of the equation is A. We see that on the right over here. And then the B subscript appears on the inside here, and it doesn't show up over here. So that's just how you know you've set this up properly. Okay, how do we deal with the directions? You know, if something's moving in the positive direction or the negative direction along the x-axis. Well, all we need to do is include that as a sign in our equation, okay? And so to finish off this video, let's do one example where we use relativistic velocity addition. So we have a spaceship which is moving towards the Earth, and it launches an escape pod towards the Earth. The speeds of the ship and the pod are 1.75 times 10 to the 8 meters per second for the ship, and 2.75 times 10 to the 8 meters per second for the pod as measured in Earth's frame of reference. Okay, so these are the two speeds relative to the Earth. What we want to know is relative to the ship, how fast was the escape pod going when it launched, okay? And then as a follow-up, now let's consider the case where the ship is moving away from the Earth and the ship launches the pod towards the Earth at the same speed as before. Now what will we see for the speed of the pod relative to the Earth? So let's go through this. Okay, so let's start by specifying that the positive x direction is to the right and the negative x direction is to the left. So we know what sign to attach to any particular velocity. When we write down our relativistic velocity equation, we need subscripts. So E represents the Earth, frame of reference. S represents the ship, frame of reference. And P is the escape pod. Okay? And what we want to know, so we want, for the first question, the velocity of the pod relative to the ship. So that would be VPS. We want to know that. So we can get it by setting up the relativistic velocity equation, which says VPS is equal to VPE plus VES, that's on top. And I know that I've set the equation up properly because P subscript is on the left side, S subscript is on the right side, and then the E subscript is in the middle. So that's how I know I set this up right. That gets divided by 1 plus the same two velocities, VPE times VES over c squared. Now let's write down what we know. VPE, that's the velocity of the pod relative to the Earth. That's positive, because we're moving to the right, 2.75 times 10 to the 8 meters per second. What we also know is that the velocity of the ship relative to the Earth, VSE, is equal to positive, moving to the right, 1.75 times 10 to the 8 meters per second. But that's actually not what we want. We want VES. We want the velocity of the Earth relative to the ship. So think about this. If you're in the ship, you're going to see the Earth moving to the left at that same speed. So the velocity of the Earth relative to the ship is the negative of the velocity of the ship relative to Earth. It would be negative 1.75 10 to the 8 meters per second. Again, if you're in the ship, you're going to be seeing the Earth moving to the left relative to you. That's what this negative sign indicates. But now we can just plug the numbers in, because VPE is 2.75 times 10 to the 8 meters per second, and then plus negative 1.75 10 to the 8 meters per second over 1 plus. Okay, one thing I forgot to write down is C. That's 3.00 10 to the 8 meters per second. So look, everything has this 10 to the 8 meters per second in it. So VPE is just 2.75. VES is minus 1.75. We need the negative sign. And then divided by C squared is 3 squared. Okay? So this works out to, comes out positive, 2.15 times 10 to the 8 meters per second. That is the velocity of the pod relative to the ship. Okay, so the other question was, now if the ship is moving away from Earth at the same speed, so VSE is now going to be negative. So we're imagining the ship is moving this way to the left in the negative x direction relative to the Earth, VSE would be negative 1.75 10 to the 8 meters per second. And VPS, since the ship is launching the pod towards the Earth still, that would be the same speed as before, 2.15 times 10 to the 8 meters per second. So to be clear, we have VSE, the velocity of the ship relative to the Earth, is negative 1.75 10 to the 8 meters per second. The ship is moving away from the Earth, but VPS, the velocity of the pod relative to the ship, is positive. It's moving towards the Earth, 2.15 times 10 to the 8 meters per second. So let's actually just draw that out, right? So it's the ship moving this way, but launching the pod this way towards the Earth. That's what's being described here. Okay, so in this situation, what we want to find is, what is the velocity of the pod relative to Earth? So in this situation, how fast are we going to see the pod coming towards us? Well, if we set up the equation, that's VPS plus VSE. Again, subscript P is on the left, subscript E is on the right, and then S is in the middle. And you have divided by 1 plus VPS VSE over C squared. So plug in the numbers. We have positive 2.15 10 to the 8 meters per second minus 1.75 10 to the 8 meters per second over 1 plus 2.15 times minus 1.75 over 3.00 squared. Again, over here what we did is we canceled the factors of 10 to the 8 meters per second, which appear in every term. Okay, you crunch those numbers and you get positive 6.87 10 to the 7 meters per second. So of course, in this situation where the ship is moving away from the Earth, the pod is going to come towards us still, but at a lower speed than before. So that's it for this video. We're going to continue on with this discussion of velocity addition in the theory of relativity, and then we'll move on to some other stuff. So I'll see you then, but as usual, take care, be safe and be healthy out there. See you later.